Okay, my name is Brian Harmer. I'm working on my master's degree in electrical engineering, specifically in the area of fiber optics. I'm working with Dr. Watt specifically, and my future thesis topic here is the development of the concept of recycling of light using optical fibers. This research topic actually hasn't been gone over whatsoever. There's no papers on it, and it's an original idea by Dr. Watt, and so there's going to be a lot of background information on it. I'm not going to be able to give you too much research data whatsoever, but this is what the presentation is going to go over, a little bit of background, the idea of light recycling, how it's going to be used, what we can do with it, the experimental setup, how we're going to design an experiment to see if light recycling will actually work, and any future directions for it. So background. First off, I don't know how many of you guys, what you guys think of when you think of fiber optics as engineers, or at least as electrical engineer. I think of communication purposes right off the bat. This concept here is going to be completely over light illumination, for illumination purposes only. So we're already actually able to collect sunlight through lenses and distribute it through buildings for lighting purposes. You can collect if you can see from this picture here, this is actually a company that does it. They have collection lenses on top of a building, and it's able to follow the sun by a tracking system and send light into buildings where otherwise you wouldn't be able to collect sunlight, like in the basement floors or in center buildings where you wouldn't be able to get it. So some advantages of this, you can filter out some unwanted wavelengths from it. Actually, you can filter out UV rays that cause sunburns or any cancer, such as that. And it cause a small invasive hole versus if you have a skylight or if you have windows, you have insulation losses. You have heat losses due to that. So that's some advantages of it. Some disadvantages, though, through sunlight. The tracking system, it's not going to be completely green. It's still going to cause power consumption for it. So if you're looking for a completely non-power consumption option, this wouldn't really work. Also, it only works when the sun is up. If you have cloud cover between the sun and your collector, you're going to get a less amount of light. And obviously, when it's nighttime, there's no sunlight whatsoever, so you're not going to get anything. And I'm honestly not sure if they do anything or if how well they'd work for moonlight. So an interesting fact that or an interesting idea I came across was you might eventually see collection farms around the globe for just collecting sunlight for lighting purposes, and only for lighting purposes only, not for any electricity purposes. So if you have a collection farm here, and you have linked up with collection farms around the globe, say China, I think it's nighttime right now, you'd be able to stream sunlight from where we are right now to China to light up places over there. So that's an interesting concept we may eventually see in the future. I'm not sure how far away that is. So some more background on the fiber itself. The numerical aperture of a fiber is what the angle of the acceptance angle that a fiber will accept light for. The larger the numerical aperture, the larger angle of light that will go into the fiber itself. So we have two different types of fibers that we can look at here. I'm not going to really talk about communication purposes too much, but I kind of have to put it in there just to compare it with what we're doing for illumination. So single mode fibers, we're actually able, for high-speed communication purposes pretty much only. They're designed for a specific wavelength. And that is the prevalent method of high-speed communications in the 90s and at least the early 2000s. Multimode, as the technology has progressed, has been becoming better and better for multiple amount of modes to go through it. But the multimode fiber has a larger numerical aperture, and that's what we're going to be looking at for illumination purposes. Onward to material types and cables. We have, if you remember from my last presentation, there's a core and a cladding to our cables. The core and the boundary between the two is where the property of total internal reflection will occur, which allows light to actually propagate through the fiber. So we have two different materials we use, are plastic and glass, and you just modify those materials to change the index of refraction, so the speed of light will go differently through them. So our different types are plastic core, plastic cladding, glass core, plastic cladding, and glass core, glass cladding. For long distance and or high speed communication purposes, you'd want a glass type. If you'd want for local area network for pretty high speed, you can get away with a glass plastic. That'd be around like the area of UNR's campus. For very short things around, such as your lab, if you want a high speed just for communications, you could use plastic. For our experiment here that I'll be talking about in a bit, we'll be wanting to use the plastic component. And this would, because this is just for a short distance, is what we'll be talking about. A little bit more here. I think this is the last little set of, talk about 3 different types of losses we deal with fiber optics. We have absorption losses, radiation losses, and we have scattering losses. Absorption losses occur when there's water molecules or any other materials within the fiber itself actually absorb the photons in the light. We want this to be at a pretty low purpose for both illumination and communication purposes. Back in the early days of fiber optics, the elimination of water molecules from the fibers was actually a big block in what we wanted to do for communications. There's actually certain bands of wavelengths we couldn't process because they'd be absorbed by the water molecules. Then we have radiation losses, which are caused by bending or kinks in the fiber themselves. These losses are, you actually cannot propagate light through an optical fiber cable if you have it at a 90-degree angle. But when you're actually laying cable, you have to be mindful of the bends in your cable itself. Scattering losses, this is what we're actually looking for illumination purposes. It's caused by the variation in material or composition or the structure of the fiber itself. When we want the fiber to emit light, such as if we want it to emit from this point here on this light to that point there, we'd want it to have a high scattering loss so light is actually emitted from the fiber. So on to the concept of light recycling. What we want to know is, can we transport light, such as the light in here, to the room next door when that room right there is dark without having a light source in that room? After this light here is already used. And that we'd be doing that by placing fiber optics cables in the walls themselves to be funneled into the other room. And this could lead to a reduction in power consumption for consumers, which would be the idea behind this. Like I said before, we would need a wide numerical aperture on the collecting parts of the fiber optics in the walls, and we would need to be using multimode fibers. And then once again, for the emission of light into the other room, we would either have a high scattering loss fiber or just have the fiber end emitting into that room itself. So the experimental setup, what we want to have is 2 enclosed boxes. We're going to have one with a light source in it, and the box will be about a cubic foot in size. It'll have 100 to 200 optical fibers extruding from each one of the walls. Once those fibers are emitted from the walls, we're going to bundle them up and then place it into the second receiving box. And then in both boxes, we're going to have photodetectors to be able to compare the lights from the source box and the receiving box. And then one more thing, the receiving box will be only limited to the light gathered from the cable itself. We're not going to allow any outside source light into that box at all. So we have some experimental questions to be answered here. Like I said before, we want to know what the percentage of light is that will be able to be transported from one room to another. We want to be able to compare the source light to the detected light. And we want to know what would be viable to use, for what lighting purposes. Would we be using it for room illumination or stair lighting, maybe even like exit signs? So we have a lot of purposes we can fool around with that. Oh, and I forgot one of the experiments, the variables that we're looking at here. We want to be able to see what types of fibers. We're going to play around with the types of fibers that can be emitted from our source box. We want to try multimode. We want to try the distances. Like I said, we're going to start off with 100 to 200 different fibers. We'll change that number around, and we're going to change also the size of the box, because obviously rooms aren't 1 foot by 1 foot in size. So those are just some variables that we're going to be switching up there. In future research, if this actually proves that it might be viable, that we might actually get some light out of placing fiber optics in the walls just by doing that. If we don't get too much, like I said before, you're able to already collect sunlight from lenses on the roof. If we were able to combine them at all, how would that do for recycling purposes? How would that do to illuminate a whole room? So that's about all I have. We haven't, like I said, we haven't done actually any research on the subject at all, so don't have too much, can tell you more than that, just like the basics of the experimental setup. So are there any questions at all for me?
How much infrastructure would it take to send light to China?
Well, I mean, we already have fiber optics wrapped around the globe as it is right now. But are you talking about like the collection farms themselves? Or are you talking about, yeah. Honestly, I have no idea. It's something further, it's just kind of an idea at the moment. No one's actually really looked into it. I don't know how much, I'm not even sure how many collection lenses like on the roof, how many you need to light a room. I just know that they're able to do it currently. So yeah, I can't really tell you the exact properties or how many, how big farms or how many you'll need to light up the entire world with just sunlight. Yeah.
Is it only applicable for sunlight, or if I want to transmit light from this room and this light to the other room? So is it possible for this kind of intensity?
So you're asking if we can send this light into, yeah, that's what this whole experiment is about. It's nothing, the sunlight part was just kind of some background information. So yeah, this whole experiment, we're just seeing if, these lights right here, we can send them next door. So yeah, we don't know if it's viable or not. That's the whole point of it. Yeah?
Both the ability of the fiber to transmit and the scattering of the light are frequency dependent. Are you going to try to fit the whole spectrum of light through each cable? How are you going to do? It seems like if you have a bunch of individual cables, each one's going to pick up one part of the spectrum.
That's part of also what we're going to see, but I think we're initially just going to have one large type of fiber to collect as pretty much, obviously we'd only want the visible wavelengths of light. So we'd be narrowed to that section at the moment. So that would be where we'd start, and then if we'd go on from there. Yeah. Any other questions? All right, thank you.
Time was 10:20. We don't have time to do another talk, so the last speaker will be the first speaker on Thursday. And the last speaker on Thursday will probably have to move on to next week.
Did you send out emails to us giving us presentations to review?
I just did that this morning. So you should have, if you did not get that email this morning, I extended the date. You give your presentation with the new slides, but the other slides are already posted. Yeah, it's too much of a hassle to make that second update. So, had you gotten me the changes last week, I could have done it, but they're already posted now.
Yes, Dr. Ray, I'm booking airplane flights for the trip to Vegas, and I did it with Department Card, but after a certain number of them, it wouldn't let me book anymore. So I have two people I still have to book, and I need a P card to do it with. I asked Dr. Wang if I could use his P card, but he said to ask you.
Okay. All right. I will talk to Kathleen and figure out what happened with that.
Well, I think it probably just reached the limit. I don't know. I already talked to Kathleen about it, and she said, well, I guess you'll have to use another card or something.
Okay. All right. How many do you have left, and
I have
what's
two
the dollar
people.
amount?
It's around $400 a person or something like that. So it'd be like $800.
Okay, I think I can do that much, but I can't afford to have mine maxed out. It brings all my research to a screeching halt. It sounds to me like this is an issue for Dr. Cornell to work out, because he's the one who insists on not having a card. But
We've been asking him to get a P card for 2 years, and he's not done it, so I don't think it's gonna happen. It's hard for us, it really is hard
No,
for
no,
us.
I understand.
Yeah, you know.
I understand. When can you do it? If I give you the card, when can I get it back? Let's put it that way.
You can get it back today.
Okay.
I mean,
Can you stop by my office in, maybe 15 minutes?
you'll be in your office in 15 minutes?
Yes.
Okay, I will be there.
Okay, thanks.
Thank you, sir.
Is there anything to do that last time you told me that my audio was not okay?
What can I do? I can have you give the talk again.
You want me to do that?
No, we don't have time for that. But I'd say maybe a third of your audio is there.
Oh, okay.
But the last half, it's not there. So